Hello, this is question 2 from the 2018 MAT. Let S and T denote transformations of the XY plane. So that's what they are. We will write, for example, TS to denote composition of applying S and T. Yeah, it's all standard function stuff. Show that TS does not equal ST. Right, so TS. So TS XY is going to be equal to T of, so what was Sx plus 1 y, and then we do T to that, and we are going to get minus y x plus 1, and then St xy is S minus y x, which is, we're adding 1, aren't we? So minus y plus 1 x, which are not the same. So that was that. For what values of n is it the case that Tn of xy equals xy for all xy? Right, okay, so we're doing multiple t's. So what's happening? Let's do t multiple times then. So if we start with xy and then we do t, then we're going to get minus y x. Then we do that again, we're going to get minus x minus y. Then we do that again, oops. Then we're going to get y minus x. Then we do that again, and we're going to get xy. So we want to have multiples of 4, and we're back to where we started. So n a multiple of 4. Okay. Part 3, show that applications of S and T in some order can produce the transformation that. What is the least number of applications of S and T in total that can produce U? Justify your answer. Right, so we got a minus 1 there. Now, have we got that from, well, so we have to do at least 1T to get a minus 1 in. I mean, we could be going to a minus 2 in there. Like you could do an x plus 1 and then an x plus 2, and then make that minus x minus 2, then add a number to it. So you've got possibilities of doing more than one s, I suppose. But we have to have at least 1t. So let's start with that then. So there must be at least 1t to get a minus 1. So that's the first thing we can say. What else can we say about it? The y is back where it started though. So to get y back where he started, we have to have at least 4 t's. But y is unchanged. Yeah, we saw this on the previous part. Therefore, must have at least 4 t's. Right, so we've got that. So, and we know we have to have at least one s. There must be at least one s to get a 1. So we've got 3 statements there. So we have to have at least 5 steps. So can we do it in 5 steps? I don't know. Well, let's try it out and let's see what happens. So say we had we don't want to start, or do we want to start with an s? Maybe what happens if we start with an s and we went to plus 1? But then if we went to x plus 1 and then just went round 4 times, we're just going to end up back at x plus 1, because 4 lots of t just takes us in a big loop. So we have to split the t's up in some way. And we can't do it after the first one either, because it would be attaching it to the y. So if we're going to be able to do this at all with 4 t's, we're going to have to put the s in the middle. It's the only way we can do it. So we go x, y. I mean, let's see if it works. I mean, it might not. Goes to minus y x, goes to minus x minus y. Then we can do an s, which will go to minus x plus 1 minus y. Then do a t, which will go to y minus x plus 1. And then do another t, which will go to x minus 1 y, which is what we want. Yeah, so we've shown we've got a minimum of 5 steps, and because we have to have 4 t's and at least 1 s. So combination of these two, so must have at least 5 transformations. And we've just shown there that we can do it in 5. So that's okay. Right, that could have been a lot worse. And yeah, we've done all that. Show that for any integers a and b, there is some sequence of applications of s and t that maps 0, 0 to a, b. Right, so this must be coming off of what we just worked out. So we've shown that we can move x up and we can move x down. So we can get to any x value. That's fine. And then we can put that to any y value. So yeah, okay. Right, that's fine. So let's get a blank sheet and try writing that out then. So part 3, well, let's just say u and s can move to any x coordinate, and t can transform any x coordinate to the y coordinate. Therefore, we can get any y coordinate too. Right, that was okay. Right, last part then. Parabola C has that equation. What is the equation of the curve obtained by applying S to C and applying T to C? Okie dokie, so we've got our original setup then. So when we start off, our coordinates are going to be x squared plus 2x plus 2. So that's where we're starting. We then transform that. That's our xy. So right, one thing that I've learned from experience on these sort of questions is that it's easy to get mixed up with our letters that we're using, the xy's, because when we transform this, we're saying this is our xy that we started at. We're transforming that to a new point. If we just call that new point xy as well, then we can get a little bit muddled in what we're actually talking about. So let's say we're transforming that into uv, into a new position. So we're going to go to a new position, which is going to be x plus 1 and x squared plus 2x plus 2. So let's say that is u, and then that is v. Then we can say then that u is equal to x plus 1 and that v is equal to x squared plus 2x plus 2. So now we need to get back into, well, what is our relationship between v and u? This is our new set of coordinates. So we got that x is u minus 1. And now we can sub that into here and say, well, v, our new y, is equal to u minus 1 squared plus 2 lots of u minus 1 plus 2. So that's our new setup, but it's now v as a description of u, our new xy coordinates, inverted commas. So we can change these back and we can say, okay, after the transformation, we can say that y is equal to x minus 1 squared plus 2 x minus 1 plus 2. It's just having the x, y, and then the uv. It just means we're not getting the original coordinates and the transformed coordinates mixed up with each other in that middle step. They are different sets of coordinates, so it's useful to have different sets of letters. Otherwise, you can just end up getting a bit confused. But this is equally valid here. It doesn't have to be x's and y's that we're using on all of these things. V and U is the same thing, which is why we can just rewrite it in that format after we've done the transformation. So we can do a similar thing then in the second part of it. So we're starting with, again, we've got our x, x squared plus 2x plus 2. We then do our transformation, our t transformation, which is taking it to minus x squared minus 2x minus 2 comma x. So we can now call that u and v, and then we can plug these things back in again. So we're saying that u is equal to our minus x squared minus 2x minus 2, and we're saying that v is equal to x, but this is now our x, this is now our y in inverted commas when we start putting these things back together. So we can now write this as x is equal to minus y squared minus 2y minus 2. So okay, it looks a little bit weird, but that is the sort of transformation that's going on in t. If we took a closer look at what t is actually doing, because we haven't really done that yet, then if we started off at some point x, y, so x, y, that's where we've started, and then we go minus y, x, so the y coordinate is x straight up, and the x coordinate is y off to the left. So it's going to be like that. So we've moved from this setup to that setup. So we've got a rotation, a 90-degree anti-clockwise rotation. So you can see if we then take a quadratic, as we've done here, a positive quadratic, you do a rotation, we're going to have something that's looking like that, which is a weird looking thing. So you get a weird looking equation. It's a quadratic, but it's now lying on its side, which is what we're seeing there when you rotate a quadratic. But yeah, using these intermediate u's and v's just to not get your x's and y's mixed up does make things a lot easier when you're doing these transformations, because otherwise you can end up all over the place. If you then write x equals x plus 1, say, on this line here, well, what on earth does that even mean? So having an intermediate u just takes that confusion away. So yeah, that was quite a nice question, that one. There was some interesting steps to take, a little bit of insight there in part 4, and a nice potentially confusing bit there in part 5 as well. So it was a nice question too.